Yes. Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel where I talk about everything I want to, science and math. And this is part 2 of AP Chemistry Unit 1, over describing matter. So, everybody, look in your notes. We had gotten to F, uncertainty of measurements. And what we're doing is we're just going over this very quickly. Hopefully you got all the blanks, but if you are missing blanks, hopefully it's just a few things and you can get it. Also, hopefully, this is all pretty good review for y'all. There's not too many brand new concepts in here, I think. Well, we'll see as we go through it. But most of it you probably studied for Unit 0. Okay, so we ended talking about uncertainty in measurements. Accuracy is how close something comes to the truth. Precision is how close several measurements are to the same value, or how finely stated it is, or how repeatable it is. So precision has a lot of things, and we usually don't know if we're accurate or not, so we just try to be precise. We try to have it repeatable, finely stated, the same value. So our little pictures here, is it going to let me pull up and down? Yeah, it is. Okay, so this one, is it accurate? One of them is, but two are not. So overall, no. If we average those three, it'd be wrong. And is it precise? No. How about this one? Is it accurate? No. Is it precise? Yes. How about that one?
Accurate and precise.
And precise. So that's what we want. When you measure, you report all the digits you can read plus one you estimate. So that was one of the things that was in your original packet, the hard one, the one I got from the mentor teacher from California. So just know that you read as many as you can, and then the last one you estimate. So it's considered your weakest part of your measurement. How to round. So 5 and up, round up. You only look to the digit next to it to decide why, because further out digits are too little to be powerful enough to round something. Why do we do this also? We want to be honest scientists and not make our data look better than it really is. How you do this is you do math using all the digits you have, and then there's different rules for addition and subtraction and multiplication and division. If you didn't have me for honors, you might not have learned this. So those of you who didn't have me, pay extra close attention that you might have just learned the rules for multiplication and division, which is that you round that answer to the number of significant figures as your number with the least number of significant figures. But with addition and subtraction, it's a decimal point thing. You look at them and you see which number has the least, goes out the least as far as decimal places go. So if you had one that goes to a tenth and one that goes to 100th, you would have to round your answer to the worst one, which is the 10th. Does that make sense to the new people? Yeah. Can you follow that? Okay, and then with multiplication and division, you round it to the one with the least number of significant figures. So we went over this. That one's got 5 because all non-zeros are significant. That one has 3 because zeros in the middle count. That one has 1 because zeros at the beginning don't count. This one has 6 because zeros at the end after a decimal point count. And that one has 2 because zeros at the end without a decimal point count. That was fast. Did y'all follow it? Everybody good with that? Okay. So dimensional analysis, that's where we use conversion factors, and this is something we're going to do the rest of your chemistry life. It's also called factor label or dimensional analysis. And how it works mathematically is conversion factors are equal to 1 mathematically because they're equal to themselves in the numerator and denominator, and anything divided by itself is 1. But if you don't understand that, that's okay. It doesn't matter. You just do it the way I say to do it, and whether you understand it or not, you'll get the right answer. So we did a problem, how many seconds to break? You copied that down in your notes, right? Nobody needs that again? Okay, so this is something new. Y'all can be happy about this. And this was on that hard study guide, is conversions using volume. If you need to convert a length to a volume, you need to cube it. So that makes sense, right? Because you got a foot, and that's a length. But if you want a volume, you'd need a cubic foot. And then it would be a box that you could pour the liquid into, right? Everybody imagines that? So like the conversion factor between inches and centimeters is 1 inch equals 2.54 centimeters. But if we wanted to know the conversion rate, if it's cubed, you have to cube it. And there's a little math thing Remember, an exponent goes for everything inside the parentheses, right? So that means you cube the 2.54 and get 16.39, but you also cube the centimeters and get centimeters cubed. You cube the 1, but 1 times 1 times 1 is 1, and you cube the inches. Does that make sense to y'all? Everybody follows that mathematically? Good, yay. Okay, so then the whole thing about the story of the atom, a lot of this came out of our other notes. I cut out the part that's not in your new book, and I added the part that is in your new book, Robert Millikan. Millikan is a big chemistry company, and I went to college in South Carolina, and they're a real big hirer. So all the chem majors, you know, were debating whether or not to go work for Millikan or not. And so there was this guy, I won't say his name since it's going on YouTube, but he was a chem major with me. And he would just do terrible in everything. Like I would tutor him all the time while we were both in undergrad. And then he would make a D on the test. But he just kept taking the test and he stayed with it. He never changed majors. And like I had another friend who was a physics major and someone had told him that if you make a C, you should change majors. Well, this guy, this was back when they still had D's. He made D's on everything. He was the 60s all the time. And never changed majors or anything like that. And he graduated. He didn't graduate on time. He had failed a few things in there too. Graduated after the summer. Got hired instantly by Millikan. And his equivalent salary of what it would be now in today's dollars was about $120,000 a year. And to me, that just says so much to you guys. One is maybe change majors if you're making C's in an easy major, but if you're in a hard STEM major, then, you know, you can still get a great job. Also, STEM majors pay more than everything else. So since then I saw a thing where it talks about STEM majors, just college majors versus earning potential, and the college majors that correlate to the highest jobs after college, the top 10 were all STEM. It was all engineering, math, chemistry, physics. So, you know, think about that. Unless you're independently wealthy, think about that major. And, you know, there's that whole thing about don't go into a bunch of debt. People end up leaving undergraduate with $100,000 in debt and then get a degree where they're never going to pay that off. So think about it before you go into debt. Also, just while we're on the little topic here, all of my kids are STEM majors, of course, I pushed them into it, but they also are smart like you guys, and they all got free college. They all got the Hope Scholarship. So y'all, none of y'all should have to pay for college. You're smart. So make sure you're doing the things you need to get that free college. Get that GPA up, get the score you need on the ACT or the SAT, and get the rigor classes. But this is considered a rigor class, so this is one of them. Any AP classes are. But just think about that. You don't need, your life will be so much better if you don't have $40,000, $60,000, $100,000 in student loans. Because that's just like being a slave to that thing. You having to always work for this thing that's out there, and you want to be free. Okay. Any questions about that on the little aside? Okay. All right. So Democritus, he's the one who gave us that term atom, which means indivisible in Greek. So he was standing on a beach. He said everything's made out of atoms, like how a beach is made out of sand. And Aristotle also said matter is uniform. So that was some of our ancients who started the conversation. And then we had John Dalton with the atomic theory of matter. He said atoms are like billiard balls, that all matter is made of indivisible and indestructible atoms. And he named it atoms because of Democritus. He could have named them Daltons, and it would be everything's made out of Daltons, but he didn't. He named them atoms, so that was good. All atoms of a given element are alike in their physical and chemical properties. Atoms of different elements have different physical and chemical properties. Atoms of different elements combine in simple whole number ratios to form chemical compounds. Atom cannot be subdivided, created, or destroyed when they are combined in or separated in a chemical reaction. And RxN is the abbreviation for reaction. Good? Okay? The law of conservation, matter and energy can neither be created or destroyed, only converted, even between each other, and E equals mc squared. The law of multiple proportions is chemicals combine in small whole number ratios. It's H2O, not H 1/2, O 2/3. And this is the billiard ball model. Next was J.J. Thomson. They had discovered a ray gun, and they realized that, that there was something to an atom that was positive and negative. So he said it was the plum pudding model, and it would be like positive goo and negative little raisins or plums. Okay, this is the one that's different from what I told you before, Robert Millikan. He did an oil drop experiment. He was able to suspend it. There's a picture of it in your book, I think. And because of that, he was able to calculate the charge and mass of an electron. So there's the electron mass, and that's the charge. That should be to exponent, not minus 19. Everybody can fix that right now in your notes. Sometimes Word doesn't like doing weird things like that. So I probably copied it. Okay, so there's our oil drop. Ernest Rutherford, the planetary model. I don't know if I spelled that right. Gold foil. It was his experiment. We talked about that. It was shocking because the atom is mostly empty space. And he came up with the idea of the nucleus, or a positively charged little nut. Nucleus is Latin for nut. Then Henry or Henri Becquerel accidentally discovered radioactivity. He was working with glow-in-the-dark rocks. Turns out they were uranium. They discovered X-rays. Marie Curie, she first really understood it. Her husband died. He was hit by a taxi cab, drawn by horses. She was the first woman to speak to a scientific community. She discovered radium and polonium. Then Rutherford discovered the 3 types of radiation, alpha, beta, and gamma. Okay, the modern view of the atom is the electron cloud. Here's our electrons. There's their orbitals. Bohr figured out that these electrons are in levels, and now we know more they're in orbitals. So protons are positive, neutrons neutral, and electrons are negative. Protons and neutrons are big, and the nucleus, electrons are little. They're around the cloud. Electrons spin. They're very small. Subatomic particles are so small they're measured in special units called angstroms. And the mass is the AMU, the atomic mass unit. Any questions? Some of that was new. Did y'all get it? Should I wait before I scroll? I see some of y'all are still writing. Okay, did y'all find that in your book? Anybody go through your book and find these? Okay, atomic numbers, mass number, and isotopes. So the atomic number, like this is boron, is 5. That's the number of protons. The mass number is the decimal number, is the protons plus neutrons. Now, this is just a little extra thing. So, like if you had carbon-12, it's got 6 neutrons and 6 protons, so its mass is 12. Where does it come from? If you look on the periodic table, it's 12.0108. If these are whole numbers, why is it a decimal? Anybody know? Nobody remembers this from honors? It's an average. It's an average of all the isotopes, and it's a weighted average. Like if you average your grades, and not everything's worth the same. The final exam is worth more than a homework, right? So it's a weighted average based on percent abundances. And also, this is another thing, is it has a little bit to do, later on you'll be doing percent composition problems, and you'll be given masses that are not whole numbers, and it has a little bit about mass being converted to energy because of E equals mc squared. So if you get to that question later and think, why are these decimals, maybe you'll remember what I told you. Okay, so isotopes can have more or less neutrons, fat or thin. Those are our cats. They're why they're on the wall over there. Some isotopes, especially fat ones, can be radioactive, like carbon-14. They fall apart, shedding particles like alpha, beta, and gamma. So now, this is the mass. The average atomic mass comes from the weighted average. So you multiply their mass by the percent abundance and add them up. And we'll be doing some problems with that. So periodic table, the groups or columns, they're vertical, periods or horizontal. And I didn't recolor this because you've got it in your notes. So everybody can recolor that from your other notes, right? Yes, sir?
Wait, what was multiplying the different isotopes
by their percent abundance.
Oh, that's percent. I don't know.
Percent. Yeah, it was. I just did the symbol. Okay, molecules and molecular compounds. Chemicals are represented by formulas like H2O. You need to memorize the 7 diatomic molecules, H2, N2, O2, F2, Cl2, Br2, I2. And let's get a periodic table so I can show you. The great thing about it, it's very handy. Where's my periodic table? There's one. Is if you look at where, oh, there's one right there. Uh-huh. If you look at where they are on the periodic table, they make a 7, okay? So it's H2, and then look over here, it's those. You see the 7, N2, O2, F2, Cl2, Br2, I2. Those are so radioactive, they don't really exist. If you look at the periodic table and see the ones whose mass is a whole number in parentheses, those are extremely radioactive things or fragile things that fall apart, and they don't really exist in real life. They're made in a lab, like the Large Hadron Collider. Okay, good with all that? So make sure you memorize those. You'll be expected to know those. Okay, the molecular formula tells the types of atoms and how many. The empirical formula is another thing, and it's a reduced formula. For example, if you have sugar, C6H12O6, there's a number you can divide into all of those. What is it? 6. 2 goes in, but we want to reduce it as much as possible, so 6. So if you divide 6, 12, and 6, you get 6, just 6 goes into itself one time, so it's just a 1, but we don't write ones. Ones are understood just like in math. So it's CH2O is the reduced formula. You want me to write that? Some of y'all are looking at me like I'm not following this. If you reduce C6, oh, that was really light. Let's get a darker one. Let's try pink. H12O6, you can divide all of these by 6 and you get CH2O. Does that make sense? It's called the empirical formula. Okay, so we're going to be doing some problems with that too in this unit. Now, picturing molecules, there is a structural formula that shows the bonds, but not the angles. So like methane doesn't really make a plus like this. It makes a tetrahedral. Remember that from honors? So you don't reflect that in a structural formula usually, okay? So ions and ionic compounds. Ions are ones that are charged. So isotopes are fat and thin. Ions are positive or negative. And how they form is by the transfer of electrons between a metal and a nonmetal makes an ionic compound. So ionic compounds are like salt, sodium chloride. Sodium is metal, chloride's not. And they attract, and because opposites attract, and stick together. So ionic bonds transfer electrons, covalent bonds share electrons, and they're between two nonmetals. But overall, compounds need to be neutral. If it is an ion, it's charged, but if it's a compound, it's neutral. So what holds an ionic compound together is opposites attract, and the metals over on that side of the periodic table want to lose electrons and become positive, and the nonmetals on that side of the periodic table want to gain electrons and be negative. And how you remember that cations are the positive and anions are the negative is looking at the pictures by my periodic table. See the cute little cats? See how positive they are and wonderful? So you can remember cations are positive, and on the other side is a terrible red fire ant. And he's very negative, so we can remember that anions are negative. Everybody got it in your head now? Okay. Now, you might be a dog person and hate cats, but you have to admit that cats are better than fire ants, right? They're terrible. Okay, so predicting ionic charges, we did this last time, is the column it is in the periodic table. So the first column wants to lose 1 electron, the next one 2, then you jump over the transition metals to column 13 over there, and they become +3. You skip carbon's family because it was normally going to do covalent bonds, not ionic. Then nitrogen's family is -3, oxygen's -2, fluorine -1, and you don't do the noble gases because they don't usually form ions unless under great duress in a lab. Okay, everybody got all of those? So it's a pattern. 1, 2, 3, skip, -2, 3, -2, -1, zip. Now, we're going to go into more detail than that, but that'll be next unit. Okay, so some ions are polyatomic. They're made of more than one covalently bonded atom, but act together as an ion. And it's great debate in the AP Chemistry teacher's Facebook page whether or not to make y'all memorize those or not. Some say, no, the students will learn them as they use them, and then others are like, no, they've got to memorize at least the most common 20. I haven't decided if I'm making you memorize them or yet not. Now you did do a quiz for me on them, I think when you were in honors, and probably Miss Korn too, right? Did she give you a polyatomic ions quiz, those who had Miss Korn? Do you remember having to memorize the OH is hydroxide -1
No.
on the test? No, you didn't have to do it?
She just let us use our periodic table.
She said just use your periodic table for polyatomic on the back, the part on the back right there. Okay, so anyway, we might memorize some, we might not. The teachers who say that you should memorize them says it will make you faster. Because just like the SAT and the ACT, the math part, it's not really all that hard of math. What makes it hard is you run out of time. It's the same thing with the AP test. What's going to make it hard is you got to hurry. So memorizing it might help you all hurry. If we memorize it, we're not doing it yet. We might do it a little bit down the road. Right now we got too many other things to learn. All right, so now naming inorganic compounds not carbon-based. So nomenclature is just a fancy word for name. And how you get the formula of ionic compounds, ions get together because opposites attract, cations positive, anions negatives. So sodium, if you look over there, it has a charge of 1. See how it's in the +1? Chlorine is in the column for -1. 1 minus 1 is 0, so that's how it's supposed to be. And so you can just write them together, NaCl. But if you have calcium fluoride, calcium is +2. See how it's in the second column? Fluoride is in the first. So you're going to need 2 fluorides to neutralize out that 1 calcium. And really, you just end up switching their charges. So it's CaF2, you don't write 1s. Everybody remember that from honors? Everybody good with that? Okay. Ionic, how to name it. If it's got 2 things, it's binary. That's the cation, just its regular name. Then the anion with where you change the ending to "ide." For example, aluminum bromide. Not aluminum bromine, aluminum bromide. Everybody remember that from honors? Good. Okay, and then NaCl, sodium chloride. Now, if it's polyatomic, the names are in a chart. Okay? And there's logic actually behind the names. A lot of it has to do with how many oxygens it has. Polyatomic cations end in -ium. If you read page 66 and 67, it'll give you some background information on their names, and that might help you remember them. And then some of the metals have been around a very long time, ancient metals, and some of them make more than 1 ion, and how they're named is it's the cation followed by a Roman numeral telling the charge, and then the anion. Or the cation has a different name based on its Latin name. Okay, so when I was your age, back in the dark ages of the 80s, we were told that the Roman names were out. Everybody was going to be using the Latin names, the Roman numerals instead. So I did not bother learning ferric, ferrous, cupric, all of those, stannous. I didn't learn them because it was the old thing and the new thing was coming. I didn't need to know the old thing, and I was wrong because I got to college and everything was still the old Latin names all the time. And even now, in the 2020s, you still see these, and so it's very good to learn them. To go ahead and learn those things. So, for example, iron can have a charge of +2 or +3. So if it's 3, it's iron 3, or 2, iron 2. But if you see ferric, that's iron 3, and ferrous is iron 2. Everybody understand that? So that gets a little more tricky when you're trying to figure out from the names, you're trying to figure out the symbol. you have to think about which one it is. So when ionic compounds form, they're arranged in crystal lattices. One unit is called a unit cell. And the properties of it, they have a high melting point, they're hard crystals. When they dissolve in water, they conduct electricity. So names and formulas for acids. For now, we will think of acids as starting with H. There's a lot of chemistry that people knew about before Dalton came along, that they just used this stuff. And one of the things they knew about was acids. So acids, they knew about them before they defined them chemically. So there's more than one definition of what an acid is. Okay, but we'll get to that more later. Okay, we're going to do a chapter on it later. But right now we'll think of acids as starting with H. And so if the anion is not polyatomic, then the name is hydro, the root word, and then ic acid, the root word of the anion. So like HCl is hydrochloric acid. So you got hydrobromic, hydrofluoric. Everybody good with that? Yes. Yes, you can write yourself a pass. I'll sign it. You be sure to sign out. So fill this out the rest of the way and sign out over there on that clipboard. And then bring me this back when you're done. Okay. All right. So if it's polyatomic and the anion ends in 8, then it's going to be the root ic acid. So H2SO4 is sulfuric acid because it's the sulfate ion. Okay? And then if the polyatomic ion ends in ite, then it's the root us. I say us. If y'all watch that video by Mark Peterson at PC, he says else. So he says else. Ite says else. But how you say this is sulfurous acid, not sulfurous acid. So I don't know why he says else. But when you get to college, just do what your teacher says so you don't look dumb, okay? If you want to say else, or us, but everybody I know calls that sulfurous acid, us, not else. But anyway, I originally used to mispronounce a lot of things in chemistry for Americans because my first chemistry professor was British. So I was learning these words new from him. And so I would just say it the way he did. I didn't say aluminium or laboratory, but everything else I would just pronounce it the way he did because he was my teacher. So some things I would say different. Okay, names and formulas of binary molecular compounds. If it's molecular, that means it's covalently bonded. And for covalent names, you use prefixes to tell how many. So counting here, mono, di, tri. That's 1, 2, 3. Tetra is 4 because that gave tetras, right? Penta is 5 because like a pentagram, the pentagon. Hexa is 6, like a hexagon. But hepta we don't talk about so much, do we? It's 7. Oct is 8, like an octopus. Non, 9, dec, 10. Okay? All right. So if the first one has only 1, like CO2, you don't say mono. Only if the second name of it is 1, then you say mono. So it's carbon monoxide. It's not monocarbon monoxide. Monoxide. Y'all remember that from honors? Good. Okay. So this would be tetraphosphorus decasulfide. Okay, covalent properties. They're lower melting point. They don't conduct electricity dissolved in water. They don't dissolve in water readily. They're volatile. They evaporate more easily. They're smellier. Okay, did I go too fast there? Or did y'all have that? I see people writing, so let's go back a little bit. Because this is the part that's a little bit newer. Sort of.
I can't really read where it says ends in ite.
Ends in ite, sulfurous acid, the root, then us acid, or Alf's acid, as Mark Peterson says. You can watch his channel on Peterson Science on YouTube. He has much better production quality than I do. Like, he has his little face down in the corner while he's sitting here showing, like, the math over here. He has, like, good lighting. He doesn't wander off of the set. He's far superior. Okay, we get on this? But you know what? I think I have more followers and stuff on my channel. See, it's not all about production. It's about heart. Okay, so organic compounds. You did that. This is not part of the honors chemistry standards, so you did not learn this in honors chemistry unless you took it like at a different school or something. It used to be part of our standards, and I loved it. It's one of my favorite parts to teach is simple organic. So we might do a little bit more with it, but this is just the general stuff. Is organic compounds have carbon. They're carbon-based. Hydrocarbons are made of carbon and hydrogen. The root of the name will tell you the number of carbons. The ending tells you about the bonds. So there's 3 kinds of endings it can have. They can be alkanes, alkenes, or alkynes. If it's an alkane, it has all single bonds. For example, ethane is an alkane hydrocarbon. Alkene has at least 1 double bond. So ethene is an example of that. And alkynes have at least 1 triple bond, like ethyne. So this is how you count in organic. We just talked about how to count in prefixes. It's different for organic. Okay, so if there's 1 carbon, it's meth, like methane. You've heard of methane, right? Okay, if there's 2 carbons, it's eth, like maybe you've heard of ethanol. Okay, 3 is propane. You've heard of propane and propane accessories, right? Propane stores. 4 is bute. It's not but. It's not butane. It's butane. You've heard of butane lighters, right? Like Bic. Oh, stop that. I don't want to update. You're going to confirm, not restart now. Okay, so pent is the same for 5. So pentane. Hex is 6 again. Hexane. Hept, heptane. Octane is what's in gasoline. Have you heard of that? Seen it at the pump, the octane rating? Non is nonane, 9, decane, 10. And it goes on up, undecane, dodecane, tridecane, etc. But you'll learn more when you take organic chemistry your 2nd year in college. So if you're a STEM major, you probably have to have organic, at least 2 years. Okay, can I go from that? Everybody got your numbers written down there? So this is our alkane, there's our alkene, there's our alkyne. Okay, so there's something also called functional groups. These are special groups of atoms like OH that can be stuck on this that changes its properties. So like OH, if you stick it, this would just be an ethane. But if I stick an OH on it, it becomes ethanol, the kind of alcohol people drink. Not me, but other people. In my family, people don't drink moderately or responsibly. They either go all out and become an alcoholic or don't drink. So I was about 14 at a family reunion, and there were all these people in my family reunion showing each other their AA chip. Do y'all know what I'm talking about? It's how many days you've been sober. And I looked around and I thought, oh no, it dawned on me. I was 13 or 14. Everybody here is either an alcoholic currently, a recovering alcoholic, or doesn't drink. I better not drink. It was a very good point in my life to decide this at 13, 14 before I ever had the opportunity. But nobody in my family drinks responsibly. Those ads, they're not for us. People go all the way to AA or to the gutter. They die an alcoholic. So I don't drink it, but other people do. It's just true. You should think about your family right now because it's genetic, I promise you. Okay, and other people, everybody in their family can drink responsibly. They can have a glass of wine at dinner and not end up driving off a bridge at 2 o'clock in the morning totally drunk. So, you know, it's just, you should think about these things. I get paid to teach chemistry. The life lessons are free here, okay? So that's one of them. All right, so that's ethanol right there. Okay, so another thing is isomers. Iso means same. Isomers have the same formula but different structures and different names. For example, C3H8O. So this is got 3 carbons in a row with an OH on it. So it is pro, and then it would end in anol, propanol. So this would be like 1 propanol. This one, the alcohol is stuck in the middle of it. So it's on the 2nd carbon, so it's 2 propanol. And sometimes these ones like this have common names like isopropanol. So you've heard of that, rubbing alcohol you can buy at the store. So those are called isomers. And I'll have to look to see how much we need to go into that for AP. I love it. I would love to do a whole unit on it, but we might, because there's a whole lot more. We can learn more functional groups. We can build isomers and all that. But I don't want to waste time if it's not on the test too much. But I know a little, you are expected to know at least that amount. Okay, so reactions. What is a reaction? It's really like a recipe for a chemical, and cooking is a reaction. So here is a real reaction for peanut butter cookies that works. A cup of peanut butter plus a cup of sugar plus an egg plus a teaspoon of vanilla. You cook it and you get peanut butter cookies. My neighbor, Mabel Johnson, made up that recipe. It's very popular now because it's gluten-free. Everybody's into gluten-free now. So she won the Pillsbury Bake-Off and got like thousands of dollars in a new kitchen, but not for that recipe, for another recipe that was not very tasty, for onion cookies. Onion cookies. She says, oh, you eat them with soup. And I'm like, no, I don't. Okay. Anyway, Mabel Johnson. So that's her recipe. So a chemical reaction is a chemical change, one or more substances being changed into something new. The original substance is the reactants, the new substance is the products, and equations must be balanced. Why? The law of conservation. So example chemical reaction is striking a match. Here's another chemical reaction, taking hydrogen gas and oxygen gas and zapping it with electricity, and you can get water. So you have to balance the equations, and these are the rules. You're not allowed to change the subscripts or the chemicals. You do change the coefficients, the numbers in front, when you balance them. So here we had the reaction originally. So you had 2 hydrogens, 2 oxygens on that side, but on this side you only have 1 oxygen and 2 hydrogens, so that is unbalanced. So to balance it, you have to make it where it has 2 oxygens over here, 2 water molecules, but then that changed it where I needed 2 more hydrogens. Now that is balanced. Does that make sense to everybody? Everybody remembers that from honors, right? So you're never allowed to insert a number between the elements in the same molecule. That will change what element you've got. So we can balance a few, an example. So let's draw on this. Draw. Okay, let's get a pen to draw on it. And let's balance a few, just to remind y'all. 1 silver, 2 silver, so there's something missing here. It's an H. Is it on yours? No. Why does this not let me draw? Draw. Then maybe I gotta pick another color. Not gonna let me draw. You're just gonna have to pretend. Okay, there's an H right there. So fill that in first. Now we can do it. 1 silver, 2 silvers. So what does appear to go here?
2.
A 2. Now we have 2 H's, 2 H's, 1 S, 1 S. It's balanced. Everybody remember that? So let's do another one. 4 P's, 2 P's. So what do we need over here? Looks like we need a 2. So now we have 2 times 5 is 10 oxygens. What do we multiply by 3 to get 10? You can't. So we have to start over. And so instead we're going to bother with these oxygens. What number does 5 and 3 both go into? 15. So we're going to start with that. We're going to put a 3 here and a 5 there. Okay, now we're going to see what that did. 3 times 2 is 6. Uh-oh, what do you multiply by 4 to get 6? You can't. So, but you go back and forth until it works out. Now, if it's tough like that one, sometimes if you balance it with fractions, you can multiply by the denominator of the fraction and you'll get the right answer. So, let's see if we can do that. 2, 2, 5, make that So that's a 3 times 2 is 6. 4 times 1.5. 4 times 1.5 is 6, right? So it would balance if we put a 1.5 here. Then the denominator is 2, double everything. It is probably that the right answer is 3, 10, 10, 6. 5 times 3. Yeah, 6. Everybody see how I did that? We will work more on that if you need it. I don't see them giving you lots of super hard balancing on the AP test. They want you to be able to use it more for super hard thermo problems and stuff like that. All right, so we'll work on those some more. Okay, so sometimes the state of matter is given, so those little S's mean solid. And so I'm going to just verbally say these. Hopefully you know them, and you can write down any you don't. What does S stand for? L, G, AQ. Aqueous. That means it's in water. Degrees Celsius. Celsius degrees. If that is written over the arrow, that means you have to heat it up to a certain temperature. Okay. CR. Crystal means you need the crystal form of it. Arrow down. It means it makes a precipitate. Something comes out as a solid. Arrow up. It makes a gas. Something's going to bubble out. It's going to become a gas. Arrow over like that. What does that mean? It yields. But you can say it makes, but it yields. So if it's got a chemical like PT on top of the arrow, what's that? Why would you add platinum to a reaction, but it's not really in the reaction, but you're putting it on the arrow? You're adding it in, but it's not really reacting. It's a catalyst. Remember that? Remember about catalyst? You learned about those even back in honors biology. You learned about enzymes. Okay, so if there's a chemical on the arrow, it's a catalyst. It helps the reaction. It speeds up the reaction. It might lower the energy of activation, but it doesn't really, it's not one of the reactants or products. Okay, arrow's going two ways. What does that mean? Equilibrium. What if it's got a triangle on top of the arrow? It means change, but what they want you to do is change it by heating it up. I don't know why, but that's what it means. Sometimes it has the word heat on top of the arrow, which once again means heat it up. If it's got something like kPa on the arrow, that's a pressure unit. You got to put it under pressure. And a little E with a dash by it, that means electricity. You might need to shock it. So that reaction we had by H2 plus O2 yields H2O, it could have had a little E on the arrow because how you make that work is shocking it. Okay, do y'all remember those symbols? If not, those are in your book. You can get them out of there too. Okay, so there's 5 reaction types. Oops, went up too much. Okay, and you need to know them. You need to be able to recognize them if they're given to you on the AP test. And so this is like something that will be on the AP test. So compounds are made in the synthesis reaction. So there was our reaction. You have 2 things getting together into one. So we can think of it like romance, and it helps us remember. So synthesis is love, 2 things getting together into one. Okay? And then if you have people get together, what else can they do? They can break up, right? So compounds are broken down in decomposition. Here's our nice little couple. They broke up. One thing broke into many things. Decomposition. Single replacement is where one thing cuts in to a chemical and the other one goes off by itself. So this is the affair. This guy comes in. He cuts in, and poor fella, he has to leave. Now, we have to believe there's true love, that there are relationships that are unbreakable. But how can we tell that in chemistry? It's by an activity series. And it is the strongest chemical is on top. And so things underneath can't replace them. And there's one in your book. It's got gold on the bottom and maybe zinc toward the top. So gold is very unreactive. It could not cut in on zinc. But could zinc cut in on gold? Oh, yes. and displace it. Does that make sense to you? Do you remember that from honors? So single replacements, you have to know if they can work or not. Do they go? And you'll have a strength chart, an activity series is what it's called. So the strongest one on top, the weakest is on bottom. Can gold replace copper? No, gold can't replace anybody. Gold's the weakest. Can aluminum? Yes. This can be used to prevent a reaction like zinc is above iron. So zinc is used to coat iron things. If you ever see something that's galvanized, it prevents rust. It makes a protective coating. The other next kind is called double replacements, where they do the do-si-do or switcheroo. You always have to have the cations first and the anions second, but they can switch between the compounds. So here you had this couple and that couple, they switched. She got the guy with the hat. She got the guy with no hat. Okay? You follow those? Now, whether or not these happen or not, it was based on solubility rules, and we will talk about that in detail in our next unit.
What's the name of the replacement?
The double replacement, yes. And we'll be doing more with that next unit. Combustion is burning and adding oxygen. Sometimes this is labeled as combustion, sulfur plus oxygen, because you're adding oxygen, but generally not. Typically, combustion is with hydrocarbons like methane plus oxygen makes carbon dioxide plus water plus energy. AP teachers say that you need to memorize what a combustion reaction is and what its products are. Why'd you go away? I bet it's going to restart even though I told it not to. That's what it looks like, isn't it? Oh, how annoying. It's been doing this a lot lately, these updates and stuff. I probably should stop the video because this is worse than my usual standard. What do I say at the end? Science is great. Like, share, subscribe. That's it.